Hey everyone, welcome back. Ready for another deep dive.
Yeah.
This time we're cracking open foundations of computer vision.
Yeah, we're going to unlock how cameras can actually see.
Exactly. We'll go chapter by chapter, pull out the coolest stuff, and, try to make it all really clear.
Get ready for some serious aha moments.
I think so. We're talking about everything from pixels to geometry and beyond.
I mean, just think about it. Like, a camera captures a scene, right? But it's really just this jumble of pixels.
Right.
Computer vision tries to take those pixels and actually figure out what they represent. It's like turning this flat image into a 3D understanding of the world.
So like how our brains take the information from our eyes and then make sense of it.
That's a fantastic analogy. And just like our brains, computer vision uses all these different cues to understand a scene. The book starts by focusing on what are called raster images. Those are the grids of pixels you see on your screen.
Right, like a digital photo.
Exactly. But the authors also mention this whole other world of vector images. These use lines and curves instead of pixels.
Interesting.
So think of it like the difference between a painting and a line drawing.
Okay.
They both, represent the same thing, but in different ways.
Yeah.
Vector images are really important for things like computer-aided design and 3D modeling. There's this whole set of techniques for working with them that they dive into in, I think it's a separate volume.
Oh, cool. So we're starting with those pixel-based images, the raster ones. What's like step one in teaching a computer to see?
Chapter 1 dives into the basics, and it all starts with computational geometry.
Okay.
It's kind of a cool idea. You can actually use geometric shapes and relationships to describe objects in an image, like breaking down a complex picture into simpler building blocks.
So instead of looking at a photo and just seeing a tree, the computer sees all those lines and shapes that make up the tree.
Precisely. And the book introduces these really fascinating concepts called Voronoi diagrams and Delaunay triangulations.
Okay.
So imagine you're taking an image and you overlay this grid of polygons on top of it. Each polygon represents the area that's closest to a specific point, like a corner or an edge. So that's a Voronoi diagram.
I can kind of picture that.
Now, if you connect those points in a specific way to form triangles, you get what's called a Delaunay triangulation.
Okay.
And these techniques are really useful for analyzing the structure of an image. For example, the authors talk about something called maximal nucleus clusters, or MNCs.
MNCs.
Yeah, it's kind of like identifying the center of gravity of a group of polygons.
So by analyzing those clusters, you can start to figure out the shape of objects in the image.
Exactly. It's like using geometry to piece together, the puzzle of what's in the image.
That makes sense.
Yeah.
But before we get too deep into all the geometry, let's talk about those building blocks we were talking about, the pixels. What's the deal with them?
Yeah, so chapter 1 lays the foundation for understanding pixels. I mean, we all know there are those tiny squares that make up a digital image, but the book dives into the different types of images you can have based on how those pixels are represented. So there's, grayscale images where each pixel represents a shade of gray. You've got RGB images where each pixel is a combination of red, green, and blue light. And then you've got binary images, which are just black and white.
Right, I've seen all those file types before.
Exactly. And what's so cool is how we can actually manipulate those pixel values to create all these different effects. It's like having this digital paintbrush.
Oh, cool.
Yeah. The book even gives some code examples showing how to access and change pixel values to, like, adjust brightness or contrast.
So it's like combining art and math.
Totally. And it gets even more interesting when you start thinking about the relationships between pixels.
Oh, okay.
So the book introduces the concept of the Rosenfeld 8 neighborhood of a pixel.
Okay.
Basically, every pixel has these 8 neighbors surrounding it.
Oh, like a little pixel community?
Exactly. And this relates to how we measure distances between pixels. You've got Euclidean distance, which is like, measuring with a ruler. And then you've got taxicab distance, which is kind of like navigating city blocks. You can only move horizontally or vertically.
Okay. So why do those different distances matter?
Well, think about how this is so crucial for things like image editing software or even self-driving cars. Understanding the spatial relationships between those pixels is essential for tasks like recognizing objects or navigating environments.
So something as simple as like how we measure distance between these tiny pixels has huge implications.
Absolutely. And it gets even cooler when you think about how we can use color to highlight patterns in an image. The book talks about this thing called false coloring, where you use rules based on pixel intensity to make certain features stand out.
Like highlighting all the pixels within a certain brightness range to
Right.
make, like a shape pop.
Exactly. And imagine applying that to medical images.
Oh.
You could make subtle variations in tissue density visible, which could really help doctors diagnose conditions.
That's incredible.
Hmm.
But how do we go from like manipulating pixels
Mm.
to actually understanding the bigger picture of what's in an image?
That's where things get really mind-bending. The book introduces the concept of representing those digital images as vector spaces. It's
Yeah.
like taking that grid of pixels and mapping it onto a mathematical coordinate system.
Okay.
This lets us apply all these powerful mathematical operations to manipulate and analyze images.
My brain needs a minute to process that.
Yeah,
But basically, we're using math to describe like the visual elements of an image.
precisely. And this framework allows us to do things like, detect edges, identify shapes, and even recognize objects. But before we jump into those more advanced techniques, let's talk about how cameras themselves are becoming more intelligent.
Wait, intelligent cameras? What do you mean?
Well, think about features like face detection on your smartphone. The camera's using sensor information to actually optimize how it captures the image. It's not just passively recording what it sees, it's actually analyzing the scene and making adjustments.
So it's like the camera's starting to like think on its own?
In a way, yeah. And the book even mentions specialized lenses, like fisheye lenses. They can capture a much wider field of view than a standard lens.
Interesting.
It's like giving the camera a superpower to see more of the world.
Okay, that's pretty cool.
Mhm.
But how do we go from those like intelligent cameras back to those geometric concepts we were talking about earlier?
Remember those Voronoi diagrams and Delaunay meshes?
Yes.
This time, instead of using random points, we're using the corners detected in the image as the generators for these meshes.
So using the camera's ability to detect those like key points in the image to then create a more meaningful geometric representation.
Exactly. And the geometry of these corner-based meshes can really help us identify objects, even in video frames where things are moving. It's like taking these static concepts and applying them to a dynamic world.
Okay, so we've gone from pixels to geometry to intelligent cameras, and now back to geometry again.
Yeah.
My head is spinning a little bit.
I know, right? It's a lot to take in. But think about how all these pieces are starting to fit together. We're building up this toolbox of techniques that let computers see the world in a way that's starting to resemble how we humans do it.
It's amazing. But before we move on to chapter 2, I need a minute to let all this sink in.
All right, ready to jump back in? Chapter 2 takes us deeper into this world of pixels and how we can manipulate them.
Okay, so we're going beyond just like knowing what a pixel is to actually playing around with them.
Yeah, exactly. Think of pixels as those tiny tiles in a mosaic. Chapter 2 is all about how we can, rearrange, recolor, even combine those tiles to create all sorts of cool visual effects. We can separate the color channels of an image, convert it to grayscale, apply math operations to change pixel values. We can even select specific pixels based on their properties.
So we have this like incredible level of control over the individual elements of an image.
Precisely. And one of the most powerful tools in our digital toolbox is this thing called edge detection.
Edge detection.
The book explains how algorithms like canny edge detection can identify those pixels that represent boundaries between objects.
So instead of just seeing like a photo as a whole,
Yeah.
we can highlight those lines that define the shapes within it.
Exactly. It's like giving the computer an outline drawing of the scene.
Okay.
And this has tons of real-world applications. Think about medical imaging,
Oh, yeah.
where doctors need to clearly see those boundaries between different tissues. Or self-driving cars, which, rely on edge detection to detect lane markings on the road.
Right. That's amazing. So edge detection helps computers see the outlines of objects. What about like separating an object from its background?
That's where a technique called thresholding comes in.
Thresholding.
Yeah, we basically set a cutoff point for pixel intensity.
Okay.
Any pixels brighter than that threshold become part of the foreground. Anything darker is the background.
So it's like turning a complex photo into this like simple black and white image where the object really stands out.
Exactly. It's like creating a silhouette of the object, making it much easier to analyze and identify.
Okay. So we've got these tools for manipulating pixels, highlighting edges. What's next?
Chapter 3 kind of takes a step back, introduces us to another really powerful tool for analyzing images: histograms.
Histograms.
Yeah, you might remember them from statistics class. They're those bar graphs that show the distribution of data.
Vaguely, yeah. But
Yeah.
how do they apply to images?
Well, instead of showing the distribution of numbers, Image histograms show the distribution of pixel intensities. It's like taking a fingerprint of the image, revealing its tonal characteristics.
So like a bright image with lots of highlights would have a different histogram than, say, a dark, shadowy image.
Exactly. And this information can be incredibly useful for tasks like, adjusting contrast or comparing different images. The book also explains this technique called contrast stretching, which basically redistributes those pixel intensities to enhance the visual clarity of an image.
So it's like taking a photo that looks a bit flat and making those details pop.
Precisely. And the book even shows some examples of how contrast stretching can actually reveal, like, hidden details that weren't visible before.
That's really cool. So we're going from manipulating those individual pixels to, like, analyzing the overall distribution of light and dark in an image. What happens after we've got a good grasp of those histograms?
Then we enter the world of image filtering in chapter 4.
It's image filtering.
Yeah, filters are like those Instagram filters that make your photos look, vintage or dreamy. But in computer vision, we use them for much more than just aesthetics.
Okay, so it's like applying special effects to images, but with a more scientific purpose.
Exactly. Filters essentially modify pixel values based on their surrounding neighborhood.
Okay.
They can be used to, smooth out noise, sharpen edges, enhance certain features.
So it's like we have these different lenses that we can apply to images to change how we see them.
Perfect analogy. And there are tons of different types of filters, each with its own unique properties. The book talks about mean filters, which average out pixel values, median filters, which select the middle value from a neighborhood of pixels, and Gaussian filters, which use a bell-shaped curve to smooth out the image.
Okay, I remember Gaussian blur from like photo editing software. It makes things look softer, right?
Exactly. And each of these filters has its, strengths and weaknesses depending on what you're trying to achieve. For example, median filtering is really good at reducing noise while preserving edges, which is super useful for things like medical image analysis.
Okay, so we've got all these tools for manipulating and enhancing images. But how do we actually start recognizing like specific objects within those images?
That's where chapter 5 comes in. It dives into these fundamental features that our visual system uses to understand what's in an image. Edges, lines, and corners.
So those are like the building blocks of object recognition.
Exactly. Edges are where the intensity changes abruptly. Lines are collections of connected edges. And corners are, points where lines intersect. We've already talked about edge detection. But the book goes into more detail about different algorithms like canny and log,
Wow.
which help us identify those pixels that represent edges.
Okay, so we're getting better and better at like pinpointing those important features in an image.
Right. And then the book revisits that Gaussian kernel, but this time focusing on its role in blurring and smoothing images.
Okay.
Think about like how you might adjust the blur setting on your camera to soften the background and make the subject stand out.
Right.
That's essentially what a Gaussian kernel does.
So we're taking those mathematical concepts and applying them to something we're all familiar with, photography.
Exactly. And then we come back to those Voronoi meshes we talked about earlier. This time, we're using the corners we've detected in the image as the generators for the mesh.
So we're using the image's own like features to create this geometric representation.
Precisely. And those corner-based meshes provide a really powerful way to represent the structure of an image, which is a crucial step towards object recognition.
This is incredible. We're really building up a sophisticated understanding of how computers can make sense of images. What's next in our journey?
Chapter 6 introduces another fascinating geometric concept, Delaunay triangulation. Imagine connecting stars in a constellation to form triangles.
Okay.
That's essentially what Delaunay triangulation does with those important features in an image.
So we're creating this like network of triangles that connect those key points like corners and edges.
Exactly. And by analyzing those triangles, we can gain all sorts of insights into the structure of the image. For example, we can look at the circumcircles of those triangles.
The circumcircle.
Yeah, it's the circle that passes through all 3 points of each triangle.
Okay.
To analyze the density of points, identify clusters.
So we're using geometry to like reveal these hidden patterns in the image.
Precisely. And this technique has applications in all sorts of fields, mapping, computer graphics, and of course, computer vision.
This is all getting very Minority Report.
Yeah.
We've gone from pixels to geometry to blurring and back to triangles. What's next on our computer vision adventure?
Get ready for action, because Chapter 7 takes us from those static images to the dynamic world of video.
Okay, so now things are moving. How does that change things?
Well, now we have this added dimension of time and the challenges of processing images in real time as they're being captured.
So it's like analyzing a flip book, frame by frame.
Exactly. And while many of the techniques from image analysis still apply to those individual frames, we also need to consider how objects, move and change over time.
That makes sense. So how do we track those changes?
The book introduces the concept of blobs.
Blobs.
Yeah. Which are these connected regions of pixels that represent objects or features within a video frame.
So those blobs are like the moving pieces in our digital flipbook.
Precisely. And by tracking the movement of those blobs over time, we can understand how objects are moving within a scene.
Hmm.
Think about how, security cameras track moving objects or how self-driving cars anticipate the movements of other vehicles.
That makes sense. And do those MNCs, those clusters of polygons, come into play in video analysis as well?
Absolutely. We can use MNCs to track the shape and movement of objects across multiple frames. Imagine tracking a soccer ball during a game or analyzing the gait of a person for medical diagnosis.
It's like giving the computer eyes that can follow the action. That's incredible. But with all these different techniques for analyzing images and videos, how do we actually start putting the pieces together to like identify and understand objects?
That's where things get really exciting. Chapter 8 shifts our focus to image and scene analysis with the goal of, recognizing and interpreting those objects within a scene.
So we're moving beyond just like seeing edges and blobs to actually understanding what those things represent in the real world.
Exactly. And one of the key tools for this is this concept of key points.
Key points.
Yeah, they're like special points of interest within an image that give us clues about the objects that are present.
So instead of analyzing every single pixel, we're focusing on those like key points that give us the most information.
Precisely. And the book discusses this really powerful technique called SIFT, which stands for Scale Invariant Feature Transform.
Okay, that sounds impressive. What does it do?
SIFT extracts key points that are invariant to changes in scale, rotation, and even illumination. This means that even if an object, appears smaller or rotated or in different lighting, the computer can still recognize it based on those SIFT key points.
So it's like giving the computer the ability to like recognize an object from any angle or in any condition.
Exactly. It's a huge step towards giving computers that ability to, see objects in a way similar to how humans do.
This is mind-blowing. And do those MNCs come back into play here too?
You bet. Remember how we use them to analyze the shape of objects based on those Voronoi diagrams? Well, we can also use them to represent the outline or contour of an object.
It's like connecting the dots to draw the shape of the object.
Precisely. And this has applications in tasks like identifying cars in traffic videos or recognizing faces in a crowd.
Okay, we've gone from pixels to geometry to blobs to key points and now to shapes. It's incredible how all these different concepts are coming together to create this like comprehensive understanding of computer vision. Where do we go from here?
Well, Chapter 9 takes a step back, reflects on the big picture, asks the question, where do shapes fit into the computer vision landscape?
That's a great question. We've been talking about shapes a lot, but how do they connect to that like ultimate goal of making computers see?
It's all about bridging the gap between, the physical world and the digital representation of images. Computer vision aims to extract those meaningful shapes from those jumbles of pixels, allowing computers to, see and understand the world around them just like we do.
So it's like we're teaching computers to recognize shapes just like we learned to do as children.
Exactly. And to do that, we need to understand how shapes are represented mathematically. The book introduces the concept of an open set in image topology.
Okay, that sounds a bit abstract. Can you break it down for me?
Think about image segmentation, where we divide an image into these distinct regions based on, color or texture. Those regions are essentially open sets.
So it's like outlining different parts of an image based on their like visual properties.
Oh, exactly. And those outlines define the shapes of objects within the image.
Wow, this is all so incredibly complex, but also so fascinating. We've really gone deep into the foundations of computer vision.
And this is really just the beginning. The field of computer vision is constantly evolving, with new algorithms and techniques being developed all the time.
Okay, so we've covered a lot of ground today, from the basics of pixels to the complexities of object recognition. Before we wrap up, I'd love to hear your thoughts on like what the future holds for computer vision.
Well, I think we're just scratching the surface of what's possible. As computers get better at seeing, we'll see these incredible advancements in fields like robotics, healthcare, transportation, and even art.
It's really exciting to think about all the potential applications.
It is, but as with any powerful technology, it's important to consider those ethical implications. Ensure that computer vision is, developed and used responsibly.
Absolutely. Well, this has been an incredible journey through the world of computer vision. I feel like I've learned so much.
Me too. And I hope our listeners have enjoyed this deep dive into the fascinating world of how computers see.
Okay, so we've explored how computer vision is like transforming everything,
Yeah.
from self-driving cars to medical imaging. But now I kind of want to peek under the hood
Yeah, let's do it.
and uncover like the math and algorithms that actually make it all work.
All right, so it's like we've been admiring this amazing machine, and now we're going to see how the gears turn.
Exactly.
So one of the most fundamental concepts in computer vision is linear algebra.
Linear algebra.
Mm.
I vaguely remember matrices and vectors from college, but how does that relate to images?
Well, think about it. Like a digital image is basically a grid of numbers, right?
Right.
Each number represents the intensity of a pixel,
Mhm.
and we can represent that grid as a matrix. And linear algebra gives us all these tools to actually manipulate those matrices.
So we're using like matrix operations like addition and multiplication to actually process images.
Exactly. For example, remember those mean filters we talked about for smoothing out noise? Well, those can be implemented using matrix multiplication. We create this special matrix called a kernel, which represents the filter, and we multiply it by the image matrix,
Hmm.
and this changes the pixel values according to the filter.
So it's like applying a mathematical formula to the image to achieve a specific effect.
You got it. And linear algebra is also used in techniques like principal component analysis or PCA.
PCA.
Yeah, PCA helps us reduce the dimensionality of data, in this case, image data, while still keeping the most important information.
So instead of analyzing every single pixel, we're finding those like key features that really define the image.
Precisely. It's like finding the essence of the image, which can be super helpful for things like object recognition, where we're looking for patterns and features that distinguish one object from another.
That makes sense.
Uh,
So linear algebra is one piece of the puzzle. What other math concepts are crucial for computer vision?
well, calculus also plays a huge role. Remember those edge detection algorithms we were talking about?
Yes.
They rely heavily on calculus concepts like derivatives and gradients.
Okay. I mean, derivatives measure how much a function changes, but how does that apply to images?
Well, think about an edge in an image. It's basically a region where pixel intensity changes really suddenly.
Right.
A derivative tells us how fast that change is happening,
Okay.
which allows us to pinpoint those sharp transitions that define the edges.
So we're using calculus to basically find the steepest parts of the image.
You got it. And gradients give us even more information.
Mhm.
They tell us both the magnitude and direction of that steepness. So they kind of paint this complete picture of the edge.
It's like using math to see details that our eyes might miss. That's fascinating. So calculus helps us detect edges. What about analyzing movement in videos?
Well, that's where optical flow comes in,
Hmm.
which uses calculus to analyze how those pixel intensities change over time.
Okay.
By calculating derivatives over time, we can actually estimate the velocity and direction of those moving objects.
So we've got linear algebra and calculus, providing the mathematical foundation. But what about the algorithms that actually make computer vision work?
Right, that's where the computational magic happens. And one of the most powerful approaches is machine learning.
Machine learning, where computers learn from data without being explicitly programmed, right? How does that fit into computer vision?
Well, think of it this way. Instead of programming a computer with specific rules to, say, recognize a cat, we can feed it tons of images of cats
Hmm.
and let it learn those patterns and features on its own. That's the power of machine learning.
So the computer's essentially teaching itself how to see a cat.
Exactly. And there are all these different types of machine learning algorithms, but deep learning is particularly powerful. It uses these artificial neural networks with multiple layers to tackle really complex tasks.
Those neural networks are inspired by the structure of the human brain, right?
They are. These networks consist of all these interconnected nodes that process information similar to, neurons firing in the brain. And by training those networks on these massive data sets of images, we can actually teach them to recognize objects with incredible accuracy.
So it's like we're giving computers a way to see the world more like humans do.
Precisely. And this is driving all those amazing breakthroughs in computer vision we've been talking about, from self-driving cars to facial recognition to medical image analysis. It's incredible.
It's really mind-blowing to see how, like, math, computer science,
Right.
and even neuroscience come together to create this, like, powerful tool. And it's clear that computer vision is still in its early stages, right?
Oh, absolutely.
Yeah.
There's so much more to explore and discover, and the possibilities are really limitless. As computers get better at seeing, those applications will only become more and more incredible.
Well, this has been an amazing deep dive into the foundations of computer vision. Thanks so much for, like, taking us on this journey.
It's been my pleasure.
And to our listeners, if this has sparked your curiosity, remember there's a whole universe of knowledge out there waiting to be explored. So keep those minds curious. We'll see you next time on The Deep Dive.